On this white piece of paper, I add yellow. And I also add magenta. And the last color is of course cyan. Where they overlap, the colors red, green and blue appear, and black. Now, when I simply invert the picture, we can suddenly see red, green and blue, and where they overlap, cyan, magenta and yellow, and white. This is mixing light colors. And this is simply the inverted version of light mixing. That brings us to this pocketbook color. With new, improved microscopic macro footage, thanks to the YouTube comments. Stupid that I didn't think of that myself. Anyway, why did they use red, green and blue instead of cyan, magenta and yellow? After all, they're not mixing light, right? Incorrect! It does the same as a light-emitting LCD screen. It has a fixed color grid, and by adding black, thus less light, it mixes the colors. Difficult to explain, but an LCD screen is doing exactly the same thing. However, in theory, you could do the same with the print colors cyan, magenta and yellow. Which is what I did in this not very lazy experiment. On the right is a pattern of red, green and blue pixels, and on the left cyan, magenta and yellow. Which is clearly brighter. But the compromise is that red, green and blue have very poor intensity, while cyan, magenta and yellow are the same. And again, that's because we're dealing with a fixed color grid here. The colors cannot overlap like on print. Speaking of print, this print gives an impression of what it would look like. So they could have chosen this in order to get a brighter display, but then the colors would be even worse. And of course they've moved on anyway to this technology that actually works like print. White and transparent cyan, magenta and yellow. Putting some liquid on top didn't work to get this display sharper, unfortunately. How do you mean you don't understand and I explain it very poorly? Have you forgotten this is the lazy channel? Anyway, this video was way not lazy enough. Let's play some music.